So let me just welcome everyone to the start of the CDY seminars for this spring semester. Our theme is pretty broad this session. We have several topics on looking at the extreme astronomical objects from X-rays to gamma rays. And we have a series of talks lined up until June 18th. So take a look at our website and the CDY Initiative pages. And as a reminder, we like to keep these talks pedagogical, and we also post readings prior to the talks. So take a look and you can engage in the discussions. And then I also wanted to announce that MPIK Heidelberg has joined us in co-leading the initiative. So I just want to welcome Jim Hinton and Brian Reville and MPIK as well. Of course, they've always, they've been very active participants in the past as well. But before I introduce Daniel, today's speaker, maybe Felix, you want to say a few words because we have several new people here, and say a few words about the CDY initiative and what we've been doing in the past 2 or 3 years.
Yeah, just welcome everybody. I see that we have quite a lot of new people here, and it probably comes from the changing a bit the topic. So we will have this semester a lot of talks on X-ray related stuff, X-ray especially. But in fact, it's not a change of topic. I think as you'll see that these objects are coming also the changing everything. I mean, actually, we've even X-ray binaries, some of them coming now. We know that ultraluminous X-ray sources like Cygnus X-ray, and I think I could anticipate that next semester we will return again to this type of object. So it's good preparation for let's say creating X-ray binaries. And then because you'll see next semester we'll have a lot of interesting talks, also at extremely high energies. So it appears that these objects are quite different that we thought before. So they could be also dominated by not simply high energies, but extremely ultra high energies. So in that sense, this semester is very important for continuation next semester, with emphasis now again to ultra high energies. Now, just probably Reshmi forgotten to mention that we, in addition to these seminars, we'll have also lectures, we'll have also the workshops like it was last year, and schools. So for this year, school is not clear still. If we'll have, then certainly we'll have only winter school, not summer school. But we certainly want to have at least one workshop, and probably that will be on Pevatrons, and will take place most likely in New York, but that we'll see. I just want to say that we'll continue this to combine the lectures with workshops, topical workshops, and schools. Yeah, I think we're just happy. We are really good now, 43 people. So it's very good for the first lecture, I guess. So we can start now, right, Rashmi?
Yeah, thank you, Felix. And I'd like to introduce today's speaker. Very happy to introduce Daniel Groselj from the Center for Mathematical Plasma Astrophysics at KU Leuven. Daniel got his PhD from Ludwig Maximilian University of Munich, and his thesis was on fully kinetic simulations of microscale turbulence in space and astrophysical plasmas. He has been postdoctoral researcher at Max Planck Institute for Plasma Physics at Garching and also at Columbia University, and he has won several awards, including the Otto Hahn Medal of the German Max Planck Society, the DOE Fusion Energy Sciences Postdoctoral Fellowship, and most recently, the Flanders Senior Postdoctoral Fellowship. So it's a great pleasure to welcome Daniel. Let's get started. The format of the talk is about 50 minutes and followed by questions. And then we also like to keep the room open for about 25, 30 minutes just to have some general discussions. And as I mentioned, we will be recording this, so please mute yourself if you're not speaking, and just send us your email if you would like to get added to our mailing list. So thank you, Daniel. You can get started.
So, There's some background. Yeah, thank you. Reshmi, thank you once again for the introduction, and thank you, the organizers, for inviting me to give this seminar today. I want to speak a little bit about how black hole Coronae power bright emission in X-rays and also cosmic rays, and in particular from a kinetic plasma perspective. So from a more kind of first principle perspective, following the discrete motions of particles in their self-consistent electromagnetic fields. The astrophysical motivation for this line of research is, as I said, is emission from black hole Coronae, in particular from two types of sources. Here on the left, I'm showing the emission spectra of X-ray binaries. So these are stellar mass black holes that accrete matter from a companion star. And here it's shown on the left the spectrum from the very famous source Cygnus X1, observed at different times. And through time, this source goes through different kind of spectral transitions. And I'm going to be interested in what is called the hard state, which is shown with the blue curve here. So it's non-thermal emission which peaks at around 100 keV in hard X-rays. And then on the right, there's also this other type of sources that I want to talk about today, and in particular super luminous, supermassive black holes at the cores of active galaxies. And here in particular is a X-ray spectrum of NGC 4151. And in X-rays, the emission is similar to what is seen in hard state X-ray binaries. But in addition to the X-ray emission, Coronae in AGN are also now potential sources of high energy neutrinos. So there is also a multi-messenger component to this line of research, which I will come to toward the end of my talk. So what is the physics, basic physics picture for how this bright X-ray emission is produced in black hole Coronae? So the basic picture is that there is a spatially compact region close to the black hole filled with hot electrons, as shown in this sketch on the bottom right. And so these hot electrons upscatter lower energy seed photons, which can, for instance, originate from a colder and denser accretion disk. And so in doing so, via this Compton scattering mechanism, they produce this X-ray emission that we can observe. But there's a number of open questions associated with this kind of picture. In particular, I'm going to argue that a lot of insight into this topic can be obtained by considering how these electrons are actually energized. And this is for two reasons. One reason is that these electrons are subject to fast radiative cooling, so there must be some quite efficient energization mechanism that continuously re-energizes the electrons in the corona to power this kind of emission. And so by studying different kinds of energization mechanisms, we might learn about the physical conditions in the corona. And secondly, there are not only electrons in the corona, but there may be protons, and they will feel the same electromagnetic fields that energize the electrons. And so there must be some partitioning of the power dissipated in the corona between the radiation that comes from the electrons and the protons, which potentially may be accelerated to high energy. And then in turn also potentially power neutrino emission. And given some recent advancement in the theory and modeling of radiative plasmas, in particular with the particle in cell method, This can be now actually done from a sort of first principles perspective by following the interactions of the charged particles and photons in the electromagnetic fields. And so the model that I want to put forward today is based on turbulence in the corona. So essentially, I'm studying how magnetized plasma turbulence powers the observed multi-messenger emission. So maybe I should say a few words about why turbulence. There are a few reasons. First of all, one may argue on general grounds based on the large separation between the global scales of the accretion flow and the small dissipative kinetic plasma scales that this flow is unstable and transitions into a turbulent state. And there's also some support for this now in terms of global MHD simulations. Here on the top right is shown one example. But of course, on the other hand, you may also invoke specific instabilities in the accretion flow that will trigger turbulence. Some of you who may be familiar with this line of research may also know that in addition to turbulence, there's been a lot of works that consider magnetic reconnection as a dissipation mechanism in the corona. So magnetic reconnection is the release of magnetic energy via rapid reconfiguration of magnetic field lines, and some of this energy is then released into particle kinetic energy, including non-thermal particles. So regarding this aspect, let me comment that in fact, turbulence and reconnection are not mutually exclusive, as it's well known. For instance, turbulent boxes have been known from simulations, for instance, and also even from some observations of, for instance, space plasmas, that turbulence naturally develops reconnecting plasma current sheets, which may be then subject to magnetic reconnection. And also isolated current sheets may evolve into a kind of turbulent state, especially in 3D. But there is, of course, a difference in terms of if you're talking about the specific simulation setups, namely typically these setups that focus on reconnection would consider isolated electric current sheets in a quiescent cold plasma, which then flows into the reconnection layer. Whereas in this turbulence scenario, you consider a kind of more volume filling dissipation scenario. So that's kind of the main difference here. And if we think about turbulence, we should first ask ourselves, what kind of turbulence is this? What is the flavor of turbulence in black hole corona? And in fact, to a large degree, this can be constrained by what we know from observations. And there are a few key parameters that enter the problem that then define the kind of flavor of turbulence in black hole corona. And one key parameter, which I will come to throughout my talk, is the so-called radiative compactness. So this is the dimensionless ratio of the coronal luminosity divided by its size. And in appropriate dimensionless units, it is inferred from observations that black hole coronae have large compactness. And so what this points toward is that there is a strong coupling between the radiation and the kinetic plasma in these sources, which involves, for instance, rapid radiative cooling of particles, or in most extreme cases, even perhaps the production of electron-positron pairs in collisions between MEV photons. And also, the corona, as is known from radiative transfer models going back to perhaps 1970s, is also moderately optically thick. So in order to explain this observed emission, you need a source that is not completely transparent to the Comptonized radiation to produce that characteristic 100 keV peak. And then in terms of more plasma kind of parameters, one key parameter, which I will also come to later in the talk, is the so-called magnetization. So this is the ratio of the magnetic energy density to the particle energy density. And for the electrons in the corona, this ratio is very large. Okay. And then there are some parameters which concern the nature of the turbulence itself. For instance, what's the typical amplitude of the turbulent fluctuations? In this talk, I will consider large amplitude fluctuations relative to the mean magnetic field in the corona. And the composition is also not strongly constrained in these sources. It could be an electron-positron pair plasma dominated composition, or it could be an electron ion, more regular kind of plasma. And here I want to present results that use this kinetic radiative particle in cell simulations, which means that in addition to the regular evolution of charged particles in their self-consistent electromagnetic fields, there's now also numerical photon particles which interact self-consistently with the electrons via Compton scattering. And there is also diffusive escape of particles from the box and injection of new particles, which could, for instance, represent resupply of particles from a cold accretion disk. And I want to split this results part into two sections. Number one is a more sort of proof of principle calculation in a 3D local turbulent box with a pair plasma composition with some application to Cygnus X1. And then in my second part, I want to focus on an electron ion plasma composition with application to AGNs. And so in part one here, I want to present this. These were the first actually calculations of turbulence in a kinetic plasma with self-consistent Compton scattering between electrons and photons. So these are 3D local turbulence boxes with under the physical conditions that we might expect in the corona, which, as I was saying, means moderate optical depth and large plasma magnetization. And here on the right, I'm showing results from this kind of simulation. On the top and middle panel show the evolution of the electron-positron and escaping photon spectrum over time. So color here represents time from blue to red. And as you see, over time, you approach a self-consistent steady state where essentially the power supply from the turbulence is matched by the escaping photon luminosity. And indeed, you obtain spectra that are consistent with observations of hard states in X-ray binaries. What can be also seen in this bottom panel is, if you consider just the global energy budget of this sort of system, is that this is a system where most of the energy is actually contained in the radiation and magnetic fields, not in the particles. So these are like the main two players when it comes to like where determining where the energy flow goes in this kind of system. And now, but what is the kind of emission mechanism actually that produces this kind of spectrum that we see here in the middle panel? And so, as I've already said, the electrons are in the fast cooling regime, which means they are their cooling timescale is even shorter than the dynamical turbulence timescale, which is required to transfer power from the large scales of the flow all the way to the micro scales, where then the energy of the turbulence dissipated and passed into particles. And here on the top right, I'm showing the turbulence energy spectra as a function of the wave number. Some of you who follow turbulence research might be familiar with that. And here there's a turbulence spectrum with this familiar -5/3 Kolmogorov or Goldreich-Sritar slope for the magnetic for the total energy spectrum. However, the new twist to this story is that once you consider the feedback of the radiation on the turbulent cascade, this is the blue curve here on the top right, the spectrum actually steepens because there is efficient radiative damping drag on the turbulent motions, which actually passes a large fraction of the turbulence power directly to the photon. So the particles actually remain to a large extent cold, and the drag on their bulk motions is what actually produces much of the Comptonized radiation under this sort of physical conditions. And as is also known, turbulence in magnetized plasmas, where there's some mean magnetic field, is anisotropic. So the motions are mostly perpendicular to the mean magnetic field direction. And as a consequence of that feature is that also the emerging emission is anisotropic. The intensity of escaping radiation perpendicular to the mean magnetic field is about 3 times larger than the intensity parallel to the mean magnetic field. But even though most of the power is lost via bulk comptonization, there is also one fraction of the power that still remains, that arrives at this plasma microscales. And this is actually released into non-thermal particles, but not throughout the whole domain, but intermittently at some special locations, which actually correlate with the electric current sheets. And this is illustrated here on the right. You can see the electron temperature in this turbulent box, and it's mostly these dark spots. It mostly means that it's cold, so particles have relatively low energies or temperatures, but then at a few of these special spots, the energy is efficiently passed to the particles and produces a non-thermal emission tail. And now where do we stand in terms of these simulations compared to observations? So here in this first part, as I was saying, as I consider application to Cygnus X1. And so here on the right, I'm showing the results of this calculation. So bottom right is emission spectrum in hard state, showing observations with orange and the green lines. And the blue is the emission spectrum emerging from this radiative particle in cell simulation without some additional post-processing of the data, just showing the emission spectrum as is the photons that leave this simulation box. And comparing this to the electron spectrum on top, you can see that the electrons are to some large degree thermal. However, at higher energies, they do develop a non-thermal tail. And this non-thermal tail then in turn sets the shape of the emission spectrum at MeV energies. What you can also see is if you look at this on top of this blue dashed curve, is that again another confirmation that the electrons are actually to a large degree cold, because this dashed blue curve actually shows what would be the spectrum if all the particles would be locked to the local bulk motions of the plasma. So mostly the peak is described by bulk motions.
Excuse me, may I ask a question? Because
yes,
I could
sure.
forget. One, you said that the the temperature should be cold, electron should be cold, but you have here 120 kV temperature. So, or I misunderstood what you said. I understand you said that the X-rays are coming from bulk comptonization, but not from the thermal electrons. But here you have 120 kV temperature.
Yes, thank you very much. So this is what I was actually trying to clarify. But what I can say again, that this 100 kV is mostly the energy not due to internal motions of the gas, but due to the bulk turbulent motions. Okay, so this is what mostly gives this 100 kV, not exclusively, but mostly. Does that make sense?
So this is the kinetic energy, is not the temperature, right?
Yeah, the kinetic energy indeed. So this is just distribution of particles in energy, which can be bulk or it can be internal energy, which includes thermal or non-thermal particles.
And the second question, where comes these electron-positron pairs? From pair production of gamma-gamma pair production, or you just assume there could be pairs?
So indeed, in this first part of talk, it's a more kind of proof of principle. So here it's mainly used for simplicity. But of course, it's been discussed, Coronae could have composition dominated by electron-positron pairs, but for this you need to include self-consistent pair creation and annihilation, which was done then more recently, for instance, by Jonas Nätila, who's also on this Zoom call. But in the second part, I present electron-ion composition, which I'm coming to next. So there you don't have this issue with electron-positron pair production.
Okay,
Does this
thank
answer
you.
your question? All right, thank you. So this brings me then to the second part of the results. which concerns now comptonization in a turbulent electron-ion plasma, and I will present an application to AGNs. So where you have these heavier ions which do not efficiently radiate, there's a few modifications to this basic picture which I just presented earlier. Namely, now the released power goes not only into X-rays, but some of it goes into the ions, which then escape the system. And so the partitioning of power between the X-rays and the ions is quantified by the so-called turbulence ion heating fraction, which in the plasma physics community is a quite well-known parameter and has been studied extensively. However, not in the physical regime applicable to black hole coronae, which are subject to this very fast electron cooling. Another feature of this kind of turbulence is that, particularly for an electron-ion composition, when you try to estimate the typical magnitude of the turbulent motions, you find that the motions are actually supersonic and transgalvanic for large amplitude fluctuations. So what you might expect in this kind of turbulence is actually to see shocks, and I will demonstrate this later. And then a third aspect is that, just thinking in terms of models and simulations, is that most of the results so far, which you might see in the literature applying to different kinds of astrophysical systems and scenarios, consider essentially a closed turbulent box. So a box which is close to particles. But when you think about it, if you continuously pump energy, of course, this non-radiating ions will just keep accumulating energy over time. So in a way, it's not a very well-posed problem to consider a closed system. So one should, I think, which I have done here, consider an open system. So where particles can actually exit the box via diffusive escape, and new ones of lower energy can enter again into the box. So it's a sort of mimicking resupply of particles from a cold disk and then escape of these particles from the turbulent corona. And of course, with this sort of box, which features the particle escape, one can obtain well-defined steady-state distributions, even in the lack of radiative cooling. Yevgeny Gorbunov at KU Leuven has been looking into that and has a paper in preparation. Here on the bottom is shown one example of his simulations from large 3D turbulent box, how the particle energy spectrum evolves over time. And then you can see that you form a well-defined steady state for both the particles contained in the box and also for the spectrum of particles leaving the accelerator, which of course need not be exactly the same as the spectrum of particles contained in the box. But now coming to radiative simulations for coronae, I have performed now more recently, these are not yet published results, simulations in 2D with an electron-ion composition, and I've studied how this energy is partitioned between the different kinds of particles and how the particles are energized. So I'm going to show you a movie from this kind of simulation. So if I play this, so let me first stop to explain what is going on here. So I'm showing 3 panels. On the left is a slice, so it's actually just the full 2D domain, the electric current. The middle is the density of the ions, and the right is the temperature of the ions. And you will see as this simulation evolves, how the ions are energized through a combination of actually shocks that develop in the turbulence and electric current sheets. So let me just play this movie. So as you see, there's current sheets forming in this flow. But in addition to that, there's also shocks propagating throughout the domain. And then they reprocess the plasma and energize the ions. And so, so this is a sort of picture of how the particles are actually energized into this kind of turbulence that we may expect in black hole coronae. And what this leads to, among other things, is that one thing is that the corona is naturally maintained in steady state at 2 temperatures. So essentially, you have electrons and the ions tend to be in steady state much hotter than the electrons, hotter by the amount of the order of the ion-electron mass ratio. And if you look at how the temperature, the kinetic temperature of the ions and electrons is distributed throughout this turbulent domain, you can see that indeed the ions are energized also at the shocks. So here on the top left, in the top left portion of the domain, there's a shock spreading throughout the domain, and you see the ion temperature rising behind the shocked plasma. But for the electrons, it turns out that they're not efficiently energized by shocks, but they are energized locally at those intermittent hotspots, consistent with this earlier proof of principle calculation at the electric current sheets. And but how does this compare to observations? And I have calculated similar as I was showing earlier for Cygnus X1. I've calculated the emerging emission, and now comparing the results to NGC 4151, which actually has some of the best available measurements in the hard X-ray band. And in fact, it's now possible to obtain really excellent fit, so to say, of observed spectra coming directly from PIC simulations, as you see here on the right. So the orange, the red, and the green dots are the actual observations, and these different blue curves to purple are what is computed from particle and cell simulations, also taking into account additionally then on top the reflection and absorption of these X-rays as they leave the corona. And I have considered different levels of the radiative compactness, which I've introduced earlier in my talk. And what is seen here is that, so I scanned from radiative compactness, which would be of order unity, which would be very much on the low energy side for what is observed, what is inferred from observation, and then I go up to relatively high compactness of about 16. And as you can see that in terms of present-day X-ray observations of these sources, the emission does not, it's just by itself, does not strongly constrain the level of the compactness, but it does affect the emission in the MEV tail, which is not, for this kind of source, well observed, unfortunately. And next, we can also look at now how the particles, what's the particle spectra, and maybe if there is some hint of non-thermal particle acceleration, especially for the ions. And what I find is then that in contrast to the X-ray emission, which does not depend very strongly on the level of the radiative compactness, the non-thermal ion spectra in particularly quite strongly depend on the compactness. Essentially, I find harder non-thermal ion spectra extending to higher energies at larger radiative compactnesses. So in regimes which are more consistent with the physical conditions that we might expect in these sources. So here on the top right is shown the ion spectra. And as you see, going from low, moderate to higher compactness, you produce harder non-thermal slopes extending to higher energies. And this inset shows the fraction of energy of the total released power that goes into the ions. And I find that a relatively large fraction of the power goes to ions, at least 50% or so, can be even slightly higher in some regimes. Whereas on the other hand, the electrons, they experience this fast radiative cooling. And so the electrons actually have only moderate variations in terms of how the radiative compactness affects their emission spectra. And so now we've learned that under the conditions.
Excuse me, another question. So that this the plot. What is the kinetic energy is for ions? So it's the same like m over mc square.
Yeah. So it's in units of mc square also for the ions. Yeah. So
maximum is at 100 MeV, around 100 200 MeV.
So this will bring me to my next slide, actually. Yes, in this sort of simulations that I have done, indeed, the maximum is not high, but it scales with the system size, of course.
No, number is units. It's MeV, right? I understand. This where is the maximum, or 200 MeV?
It would be no. Actually, it's higher, right? It's
Is it mass of protons Z squared? Is it?
Yeah, it's mass of protons. Yeah, so basically the iron Lorentz factor is around 100. Like the maximum Lorentz factor is around 100.
Yeah, just my question was not MC square is now not electron mass but proton mass.
Yeah. Sorry, yeah. So yes, indeed. And so yes, and so as I was saying, so basically, this is I find that under the conditions which give emission spectra consistent with X-ray observations of in particular, for instance, of NGC 4151, we also find efficient production of non-thermal ions. And as has been discussed quite frequently in recent literature, now extending these results to much larger systems, extrapolating essentially, we may be able to explain how these non-thermal ions and protons produce via chain of hadronic reactions, or also TeV neutrinos, as we now have measurements of ice cube from sources like NGC 1068 and also including NGC 4151. And Rostam Mbarik at University of Maryland has now followed up on these calculations, more recently using a kind of model or setup, if you like, similar that I presented earlier, but used specifically for trying to study non-thermal acceleration of ions, essentially simplifying a little bit, or actually neglecting the radiation treatment for simplicity, but still using this kind of open box with particle escape to obtain steady state distributions. And he makes a number of arguments for how this spectrum might extrapolate to much larger system, essentially. And here on the bottom is shown now a recent calculation following the predictions for NGC 1068. And these estimates look, in fact, quite promising, which leads us to conclude that turbulence may be able to power not only X-ray, but also neutrino emission from this kind of sources. And then maybe I can also just reiterate on this point that one key parameter that here comes from the plasma perspective is that, of course, not all the available power goes into the X-rays, into the ion side, but also some goes into the X-rays. So, and we need to note what's the ion heating fraction to have some confidence on what kind of luminosity we might expect from neutrinos. And models favor large ion heating fractions, which are broadly consistent with my results, which I just presented. So yeah, and this actually already brings me to my conclusions. I wanted to keep it brief today to allow more room for discussion. So so I have shown that this is now following recent advancements in terms of particle and cell simulations in radiative plasma. We can study how particles are energized and how the emission is produced from first principles. And here I focused in particular on a turbulence energization scenario. And I've shown that turbulence may be in fact a viable mechanism for powering the high energy multi-messenger emission from black hole coronae. And what plasma physics can tell us, for instance, is how this available power is partitioned in some non-trivial way between the X-rays and the ions, which may be non-thermal, as I find. And last but not least, there's also opportunity to apply this sort of capability to other types of radiatively dense environments, where there's strong coupling between the plasma and the radiation. And one such example is, for instance, the prompt gamma ray burst emission. As is well known, gamma ray burst jets may feature, for instance, turbulence, but they also feature very intense radiation, where this sort of effects might come into play similarly to black hole coronae. So thank you very much, and I will take questions.
Thank you, Daniel. Thank you for the excellent talk. Questions for Daniel? Henrik, please go ahead.
Just like, it seems like if you look at X-ray polarization, you should find out how good this bulk quantization works. So, like, it's a pretty good diagnostic for these kind of comparing simulations to observations.
So yeah, thank you very much for the question. I have not looked at polarization yet. In principle, this sort of model can be also extended to calculate the X-ray polarization. But maybe just to be totally clear and honest, I think that in terms of X polarization, one major factor that determines the polarization is also the geometry, the global geometry of the corona. And so these are local box simulations. So I think there might be also some limitations due to that. Of course, there is a mean magnetic field, which gives this anisotropy even locally, but I think that this is something maybe to keep in mind here.
Thanks.
Okay, Xiao, you're next.
Yeah, thanks, Daniel. Yeah, before I ask a question, I want to clarify about this anisotropy in original GS95, and they use the round reference frame of the mean magnetic field. And in fact, this anisotropy should be measured in the local reference frame of the local mean magnetic field. So my question is, so you mentioned that the particle get energized near the current sheet. So I wonder, is the acceleration mechanism reconnection? And is which component of electric field parallel, perpendicular? Is a parallel dominate the acceleration?
Yeah, thank you very much. So I think there were two questions. One is the anisotropy of the turbulence, and the other is the
no, sorry. The first is not a question. Just I want to clarify that a bit.
Okay, thank you. I'm very well aware of the local anisotropy feature. I've done some calculations myself of this, but the thing is that here I'm calculating the photons that actually leave the box, and so for this does not make sense to consider a local kind of anisotropy, because you need to consider like just a fixed frame and just the the photons that leave the box. That's why. But if you consider something that's within the turbulence, a turbulent eddy, then yes, indeed, one should look at the anisotropy relative to the local magnetic field. Does this make sense?
Right, I agree. Yeah, I understand. And I think also for observers, it's really for them to define what is local. Yeah.
Yeah, for sure. Yeah. I mean, there is maybe some arbitrariness in now saying what is actually the mean field and what kind of scale of the corona should you define it. Yeah, it's a good point.
Yeah, but I just want to clarify some. Yeah, so because some people, when they read the original GS95 paper and they just took the mean field from the original paper. Yeah, so.
Yeah, good point. Right. But your second question, going to the electron energization, so I think one should distinguish ions and electrons. But if you're asking in particular for the electrons, which power the X-ray emission, it's really a key point that they're subject to this very fast radiative cooling, which then makes this secondary energization by this perpendicular electric field a little bit harder to compete with the fast radiative cooling. So I think in my simulations, at least, it's the acceleration along the magnetic field by E parallel that produces non-thermal power law of some limited extent. I have made some estimates that perhaps if you were to extrapolate this to much larger domains, there could be some contribution also from a more kind of stochastic type acceleration. But this is beyond what I can probe with my kind of kinetic boxes.
And for protons, is it a bit different?
For protons, it's different. So for protons, they may be injected into the acceleration mechanism, so to say, via reconnection, or as I see here in this latest simulations, also at shocks, in fact. But then the subsequent acceleration, to higher and higher energies, I think it's mostly kind of stochastic type acceleration, that you would usually study in kind of turbulence.
Okay, thank you so much.
Maxime?
Hello, nice talk. Could you clarify a few points? It's like a very big simulation, but how big is physically your volume, and how long is physically your simulations are?
Well, I guess it depends on what kind of units you want to specify that, right? So what is natural kind of units from a plasma perspective is that you count the size of the box in your plasma microscale, so to say. So basically, in terms of plasma skin depth, so this would be the ion skin depth if you have an electron-ion composition, or the pair plasma skin depth if you have pair plasma composition. So these simulations, taking that unit, they're like a few hundred skin depths in size.
I mean, Corona scales.
Well, for
Physical
Corona
scales.
scales, it would be many, many, many orders smaller if you were to say like in centimeters.
Yes, and what I see, your simulations, not all volume is affected by multiple shocks propagation, and it looks like you simulate relaxation process in a plasma, not final result. Am I right?
No, I think these are what you can legitimately call as, if you evolve for long enough, steady state spectra. So when you set up the simulation, of course, you need some time for the system to relax in a steady state. But even in steady state, I see shocks. But there is an interesting point that these shocks in steady state are weaker than at the very initial time, because at the very initial time you have these initial perturbations which are very far from pressure balance, and also you have very cool ions, which then makes the sound speed very high. But as the ions actually heat up to mild relativistic temperatures, you have actually also, for the motions in terms of the sound speed, you have actually transonic motion. So it's kind of like weak shocks in steady state. This makes sense.
Thank you.
Hi, Evgeny.
Thank you, Daniel, for the talk. I have actually two questions. One is technical. You said that you power turbulence somehow, but what's the actual way you do it in simulations? How do you power the turbulence?
So there's a few different ways to do that. What I use is I impose an external time-varying electric current through the domain. And this current is basically imposed at the largest wave numbers of your box. And it has some kind of frequency and spread around the frequency, which is of the order of the lowest frequency Alvin wave that fits into the box. And this is something which has been used quite often, let's say, in this sort of kinetic plasma turbulence simulations, but one could imagine different kind of forcing mechanisms.
Mm-hmm. And the second question is, I'm surprised by the fact that whatever you do with parameters of the simulations, you basically obtain more or less the same spectrum of the photons. So there must be something universal about these numbers. And I wonder if you have something in mind how to estimate this quickly, kind of rule of thumb to calculate the numbers.
So yeah, thanks. That's a great question. So so a few clarifications. There is so there's actually three parameters for this problem from the point of view of my local model. One is the optical depth, which is set to order unity. The second is the magnetization of the plasma, and which basically determines how non-thermal your particles might be, subject to fast radiative cooling for the electrons. But then there's a third parameter, which is the rate at which you pump soft photons into your domain, which are supplied, for instance, from a cold disk. Okay, and actually the soft photon rate does affect the emission spectra quite a lot. So what I've done here is basically I've tuned this soft photon ejection rate to produce a spectrum which is consistent with observation. So basically, the so-called photon amplification factor, so basically the ratio of the escaping photon energy to the soft photon energy, this can be tuned by setting an appropriate rate of photon injection. This can be estimated even analytically. I have done that. And so basically, these analytical estimates give you a first guess of what this soft photon rate should be, up to order unity correction factors, which then need to be a little bit fine-tuned.
Okay, and then to extend it slightly, if in fact there is a range of the numbers that you can obtain varying the parameters, then what is this range? How far you can go from 100 keV?
Okay. Well, I think so I've had there's three main parameters. So it depends on like what are you hoping to achieve. Okay, so for instance, if you think about just the peak of the emission, this is set by the effective electron temperature, and this is still largely determined by the optical depth. So there's this well-known relation that basically the electron temperature drops with the optical depth. This is for unsaturated comptonization. And so basically this is still the main factor. So if you want to push, for instance, the peak to even lower energies, you want to increase the optical depth. If you want to push it to higher energies, you can reduce the optical depth. And then there's this other parameter, as I say, which is this the soft photon rate, which actually can push the spectra around quite a bit. Especially when you approach this MEV range, there's a sort of like runaway effect, because, you know, as you get into the Klein-Schiner regime, you know, the scattering weakens and weakens. So like if you lower the soft rate below some fraction, you know, like it can quickly go to very high energies, essentially.
Okay, thank you.
Thank you. Daniel, I have a quick question. So these sources, there's been some interest in searching for neutrino emission from hard X-ray bright AGN and looking for correlations with high intrinsic X-ray flux and non-jetted AGN. And NGC 4151 is actually one of the sources that was associated with some neutrino evidence of.
Right, exactly.
I was wondering, you know, and in your simulations, you're looking at the proton and electron fractions, and you have a high proton, I think you said above 50% ratio. So wondering, are you able to predict anything about neutrino emission?
So right, so the current state of the art of results that are somewhat related to what I presented using this kind of simulation setup is basically on this plot on the bottom here. But this is for NGC 1068. Rostam and Barik, who's leading this effort, has not done calculations specifically for 4151. Of course, the main reason to focus on NGC 1068 was that there are best measurements from IceCube available for this particular source, which in turn give best constraints on the inferred proton distribution. That's why it makes sense to start with 1068 first and then maybe extend to other sources, and 4151 would be the next logical target. But of course, from my point of view, looking at the X-ray emission and then connecting that to the X-rays, NGC 4151 is a very good source, because by far the best measurements in X-rays are for that source. So you want to look at the source which is very well observed in X-rays to make this connection between X-ray and neutrino luminosity, for instance.
Yeah, you need sources. I mean, NGC 4151 has really excellent NuSTAR data.
Exactly.
And so there could be other sources with NuSTAR. I mean, you really need the hard X-ray, I think, emission data.
Yeah.
Okay, thank you.
And maybe I can also add that, you know, in principle, it would be very helpful in terms of constraining different scenarios to have good measurements also in the MEV range. But unfortunately, for AGNs, this is not available, but it is to some degree for X-ray binaries, at least for Cygnus X1 and a few other sources. And that's
correct. And I think that the old COMTEL measurements just didn't have the sensitivity or even, BATSI. But maybe in the future, there will be MEV measurements, which will be helpful.
This would be very exciting for my line of research, yes.
Can I follow up on this? Sorry.
Yes, go ahead.
Hi, Daniel, it's Amir.
Hi, Amir.
The black line is the photon spectrum you actually get, all the way down to GeV.
So it's basically, so what Rostam has done is basically using this sort of turbulent box setup, but without some treatment of radiation, but allowing for escape and trying to see how this how the spectra extrapolate to ever larger domains. And he supplements this.
My problem is the low energy domain, because this spectrum you can readily rule out for NGC 1068. It will largely violate energy budget. You need a break at around 1 TeV to be consistent. So the way Martin Lenoir overcome this, he claimed that, you know, there is like regulations, feedback. The cosmic rays kills the turbulence.
It's not a black line; it's a black region, and so on the bottom of this range, there is actually sort of a break or steepening of the spectrum, as you see.
And what produces this break?
So basically, the argument is that if you extrapolate the spectra that have been seen in some of these peak simulations to much larger domains, there may not be just a clean single power law slope extending all the way from injection scale down to the maximum energy. But what may happen, in fact, is that at the highest energy, you have steeper spectra, and how steep they are depends essentially, among other things, on the plasma magnetization. And then as you go from this largest energy towards the low energy range, you get to a slope which is more like -2.
No, but you need like on the E and E scale, you need something that increases like 1. You need much harder in order not to violate energy. And Martin actually produces this by claiming that the feedback of the cosmic rays actually kills the turbulence. But the problem there is that this cannot, this completely suppresses electron acceleration. So it cannot produce both, the protons and the electrons. And I want to run you over.
I'm somewhat familiar with this, that of course there's been quite a few recent works, some of which are on this slide that consider acceleration in the corona, and indeed some of these have invoked very hard spectra like -1 at lower energy range. But this one now, the latest result, which uses some of this modeling, is a little bit different. So, but I'm not.
Well, but it might be that you don't wait long enough to actually see these effects.
Actually, it's good. A bit different representation of the density. Do you understand this is the dN over dE multiplied to energy? Because it's not clear what means centimeter -3. It's just differential distribution multiplied to energy. Am I right?
I think it's just dN over dE, but I'm not.
No, if dN over dE, then it should be per energy, right? Per GeV or whatever. And since that is missing, so I assume it's just multiplied.
Okay. Might be, yeah.
Because I mean, if then we apply another E, that I think what Amir is asking, I mean, we'll see what is the maximum. Of course, we could estimate now as well. However, that would be really useful to have this E squared dN.
I compare this to the orange line, which is the, what you need for the ice cube production. So,
but before going to ice cube, I mean, just better to understand what is what the plot is now, because it cannot be centimeter -3, right? Or it's integral density above some energy. So that could be useful to know. I mean, otherwise it's not very clear. So is either density at energy above some energy and above E, or dN over dE multiplied to E. One of these options, I think, should be here, right?
Yeah, I don't know to answer. These are very fresh results. So yeah,
it's only technical because it will tell us what is the maximum, and then what Amir says, you need a break, whatever. Yes, then you could estimate the total energy.
This is the number of protons per energy, because the slope is -3, by I at least.
No, but what is it the dN over dE? multiplied to
Yeah.
E, right?
This looks like the N over the E. Yeah.
Yeah, I think it. Yeah, I think so.
Then,
This
But
looks
then
like the
the,
N.
that, yeah,
be, units should be different. Then it will be GeV minus 1.
well, maybe
Yes.
labels are just not. It could be that the labels, need to be.
No, the units are wrong. It's
Yeah.
a typo.
So I think it's just, yeah.
It's like,
I think it's more the units than the. But yeah.
okay. Anyway, thank you.
Yeah, I'm sorry. This is very fresh results, so still ongoing. So I'm sorry that I could not give further details, but it will be all in upcoming paper by Rostam.
Yeah, looking
Okay, so
forward to it.
Very
Looking forward.
important, I think, anyway, just to see.
Felix, you want to take on? I think we don't have any more questions directly related to the talk, but maybe you want to just have some discussions?
Yeah, maybe it just came to my mind with this density question. What is the total density of the protons? I mean, okay, we'll see what is that, but did you compare the density in the case of the classical accretion? I mean, in Corona, you have I believe you have a less density, right? Than if you ignore all this turbulence, you take the classical accretion picture. What what is the density of the protons?
So how I like to think of this is in terms of these dimensionless quantities, like for instance, the plasma magnetization, which includes in the denominator the density. So if you're talking about this application to neutrinos, typically you find more favorable situations when the magnetization is relatively high, like order unity or so for the protons, let's say, which would actually mean that the corona would not be completely electron ion, but would be actually a mixed composition plasma where the number density would be dominated by electron-positron pairs, but the mass density would be still dominated by the ions. I'm not sure if this answers your question, but this is what I can say from regarding that.
It's not just question. I think it's just it's my opinion, personal opinion. I think it's before going all this neutrino-related stuff to build around this. I mean, you have to first of all to be sure what experimental results are. I think it's a bit tricky to build the scenario picture just to explain neutrinos, which may exist, maybe not. So that was, but the general picture is very interesting. So that was I want to discuss now. In the in ADAF or just classical to temperature accretion plasma model, proton temperature could be up to 100 MeV, and electron temperature could be something like 10 to 100 times less.
Yeah.
So unless you assume some plasma waves which equalize quickly, otherwise there is no way to equalize temperature between electrons and ions. And now what I saw, that was my question, was what I mentioned, that so I see that you have almost in your picture, your energy in protons is 3 orders of magnitude higher than in electrons,
Yeah.
right? Because
Yeah.
that is interesting. That because it means even more I mean, from first principles, yes, temperature should be 3 orders of magnitude more. I mean, ME, but then you equalize you change the transfer energy of protons to electrons, and then in the extreme case you make equal temperature for electrons and protons. But here you naturally get absolutely two different temperatures. And in that sense, I mean, again, I don't know where so is a general, I mean, so be excited with these neutrinos. I mean, but then you could calculate something more interesting thing, actually. You could calculate this because you have a steep spectrum like pi zeros above 100 MeV or above 1 GeV. You have steep, that was my second question. What is this plot? Is the N over dE or the N over dE multiplied to E? Because you have a steep spectrum, then you should expect And sensitivity for Fermi, in fact, is much, much better than sensitivity of ice cube. So if you have steep spectrum, certainly you should see that at the GV energies. And if you don't have data, it does mean that you have limits, or maybe even there are data. So I think what you got is extremely interesting. And just to reduce that to explain neutrinos, I mean, it is a bit, well, very personal view is early.
GV photons wouldn't escape this region. It's a compact region, so you can't possibly observe much at GV.
No, GV, it's in maybe binaries where GV interacts with, okay, TV. GV interacts with the X-rays, but then you have a TV which will escape because then cross-section is much less. But at any rate, this is necessary. Just even they don't escape, they will initiate cascade. So the energy will not disappear. So in that sense, I mean, if your energy is basically sitting at the GV energies, then you should calculate the radiation, even if say it absorbed, but absorption does mean disappearing of radiation, right? You should create cascade, and that will come. So maybe the 1 MeV at the end. Anyway, so just, this is very interesting picture, and even more extreme that to temperature plasma, and that will be interesting to investigate. Actually, another very interesting thing, if you have such steep spectrum, is the gamma ray lines. That is another very interesting thing you could expect. And the gamma ray lines could give you measure a lot of interesting. So we had with CDY some paper more than 40 years ago into temperature plasma gamma ray line emission, and recently we revisited that. I think Maxim is here, Maxim Barkov, but we were calculating that for Maxwellian distribution. So it will be very interesting. Anyway, what I want to say, there are a lot of interesting observational consequences could be here, and that will be not the best just to go to neutrinos, very shaky results, and the very shaky energy band, as Amir mentioned, that because of energy conservation law, you have to break, probably, I'm not sure, but probably you have to break your this distribution. And if you break at 1 TeV, then of course, no neutrino will appear there. And that is, again, from the first principle for energy conservation law, you have to break. But it's very, very interesting. I mean, actually, you could get much more interesting things just only simply reducing the neutrinos.
Yeah, thank you very much, Felix, for these suggestions and comments. For sure, there's broader applications here to explore than just neutrinos and X-rays for sure. But I just wanted to focus here now as a start on these two aspects. But certainly there are other things to see here.
No, it's just, I'm not criticizing. I'm saying it's a very interesting, very exciting, a new way to get energetic.
Yeah, I wasn't taking as a critique, no.
Yeah. So any other issues you'd like to discuss? We are only 25 people now, but maybe some.
I can ask a question if you want, if nobody else.
Sure.
Yeah.
In phenomenological models for these sources, the compactness is one parameter for electrons, but the other main parameter is the soft photon compactness, which is kind of your injection rate. And it's usually, until pairs come in, it's the ratio of electron to soft photon compactness, which really controls the shape and the amplification factor. And you have to put an optical depth, but so you fix the optical depth, and then the ratio of LE over LS, we'll call it, that makes the spectral shape for the most part until you have pairs. So and the LS, once you fix the source size, sets the cooling rates and everything like that. Is it pretty much the same? And you just do you think, if you rephrased it that way, if you took your soft photon injection?
It is actually pretty much the same. Yeah, I would I would say from that point of view, nothing changes. What is, of course, different here is that now you calculate self-consistently how the electrons are energized. So the electron temperature is just, calculated self-consistently. So to say, and also may include contributions, for instance, from bulk motions, as I was saying earlier. But yeah, if you just look at it as a radiative transfer problem, so the plasma is a black box, essentially. I don't think much changes. But what this black box can tell you, for instance, is what happens to the non-thermal particles, how this dissipation takes place, and things like that.
Yeah, no, I agree. That's important. And one other question I never understood, like at the workshop, Lorenzo gave a talk. What sets the scale for the bulk motion? Because you could think it's some radiative deceleration. It depends on the radiation field. Why 100 kV or Lorentz factor sort of moderate 1.5 or something like that for the bulk motion?
It's actually quite straightforward. It's largely determined by the Leuven speed. So it's actually not exactly a universal result that it must be bulk motion. So basically it favors bulk motions when you have high Leuven speed. High Leuven speed for me means high magnetization, and high magnetization means very high compactness. So you favor the bulk motions emission scenario at very high compactness. At low compactness, it's more of a kind of thermal comptonization scenario.
Okay. Yeah. But is there a way to get the scale out, sort of what Evgeny was saying, some parameter to understand why?
Well, it's basically, yeah, it's how the Leuven speed is scales in units of C. So basically, yeah, you need this mild relativistic Leuven speed, essentially, like to get this to 0.2 MC squared or something like that.
Okay,
so
wow. Okay, that's cool. Maybe following up on something you mentioned but didn't say. So how important is the guide field? Because the guide field can crush the reconnection or change everything depending on or how disordered it is. So.
Yeah, that's a great point. It does affect things quite a lot. I have not done a lot of calculations for strong guide field, but a few. But it's not surprising. It's consistent even what other people have found in non-radiative simulations or with simulations maybe in optically thin regime. Guide field basically kills non-thermal particle acceleration. So basically you just get plasma heating in a sort of way. So that's the main difference. And here I'm basically focusing on this large amplitude, so basically order unity guide field. So fluctuating to mean field is order unity because this is the regime which favors non-thermal particle acceleration. Of course, I'd like to explore regimes where we might see efficient particle acceleration.
Yeah. Okay, that's cool. And then I could have one more question, but does someone else want to go? Yeah, Brian. Okay.
Oh, yep. Hi, thanks. Great talk, Daniel. I just before, because related to what Paolo just said, I mean, one thing that always concerned me with these things is the scale separation. So if you have a guide field, but then you're injecting at a much larger scale, then as far as by the time it cascades down to the size of your box, there's probably not a huge amount of power in it, or there will be a very different power. The larger you increase the scale separation, the less power you would have on that scale. And then do you think this would slow down the whole process or change things dramatically? I mean,
well, yeah, I mean, as I was just saying, it will make non-thermal acceleration much less efficient, much slower. So basically, it slows down everything. You can also view it from this sort of perspective. So yeah, it's.
Do you see hints of that as you make your simulation boxes bigger?
Oh, you mean you're talking about dependence on the size? Okay,
Yeah.
sorry. Okay, all right, sorry. All right. So let me put it this way. So there is some belief that actually things do scale up with size nicely. One supporting argument is this latest results that were also focused on this neutrino production that support this. Why it's so physically, I think it relates to plasma turbulence intermittency, essentially. So some of this turbulence intermittency theory is basically what they say is that, at every scale, you have a distribution of the amplitude of the turbulence fluctuations. And the most intermittent structures actually preserve the fluctuation amplitude of the outer scale. That's at least what intermittency models also compared to some simulations seem to be suggesting. So, and I think the intermittency plays a really quite important role in setting the rate of particle scattering and the acceleration. So I think maybe you can get away with invoking intermittency essentially. But it's something that's, you know, subject to ongoing investigations.
Yeah. Okay. Thanks.
So I think we've had some excellent discussions. The room is open and available for people who want to stay on for a bit more. But I just want to close the session formally for today and thank Daniel. Really excellent talk, and you can see very fruitful discussions. And looking forward to your paper that you're working on.
Yeah, thank you very much.
So if there is an interest for people to stick around for the next 10 minutes to talk to Daniel, depending on if he has time, the room is open. Otherwise, hope to see everyone again in 2 weeks. Thank you very much.